Okay, so next let's talk about matrices. So just a quick review of matrices. So a matrix is a rectangular array of numbers, and here they're going to refer to the elements like this. So they're going to use a capital letter for the elements. A little bit unusual, but that's what they're going to do. And we have I and J, which we stand for the rows and columns. And then we have the size of the matrix, and we denote it as m by n, where m is the number of rows and n is the number of columns. And we have an operation of adding two matrices, and so we take two matrices and we get a new matrix, and in order to add them together, they both have to be of the same size. And then to get the individual elements, which is what this stands for, the individual elements, you take the individual element of the first matrix and the corresponding same element of the second matrix and add them together to get the result. And you do that for each element in the C matrix. And then also we have a multiplication of matrices. It's not a scalar multiplication. We also have a scalar multiplication that we can define for matrices, but right now we're not talking about that. But we do have a matrix multiplication where you take two matrices and multiply them together, not a matrix times a scalar. So here we take A and B and we'll get a new matrix which we'll call C. And the size, now we know that if A is an m by n, then in order to multiply it by a b on the right-hand side, then b has to have n as the first dimension of its dimensions, or in other words, the number of rows here has to be n, and then p can be anything. And then we're allowed to multiply the a and the b. So the n here of a has to match the n here of b. And the resulting C matrix will then get its size from the M here of A and the P here of B. And to actually accomplish this multiplication, when we multiply A times B, we can ask, well, what are the elements of C? What do we actually have in C? We know what the dimensions of C have to be, but what are the individual elements? And again, here they're using capital letters to denote the elements. So if you want to know what the ijth element is, you do this. And what does that mean? We're going to take something from A and something from B, and we're going to multiply those. Those are two elements, one from A and one from B. And then we're going to get another element from A and B and multiply those, and we're going to keep doing that, and we're going to sum up the results. So which elements? So here we can see we're summing over k, so that is k becomes 1 and this k becomes 1. And then we take the I and the j. If we want to get the Cij, we know what I will be and what j will be because we're talking about getting the Cij element. So that's fixed. And then we put in k equals 1. This gives us a result. And then we put in k equals 2. That gives us a different result. This is, by the way, this is just a single element. In other words, this is just a scalar like a real number, and this is just a scalar like a real number. So just multiplying two scalars together here, and then we when we put in k equals 2, we're multiplying a different set of scalars, and then when we put in k equals 3, we're a different set of scalars, and we keep doing that all the way up to k equals n, where what is n again? N is this matching the number of columns in A and the number of rows in B. And so we just keep doing that all the way up to n. We'll get a string of things that we add up, and that will give us this. Now here's a picture I've never seen before, apparently from Wikipedia. So here's A and here's B. Remember that the number of columns of A has to match the number of rows of B, and number of columns is 2, number of rows is 2, so that works. And then the size of the resulting matrix will come from the number of rows of A, and that's here, and the number of columns of B, that's here. So that's a nice diagram. And then to know what this particular element will be in, this is C here, so to know what this particular element of C is, the diagram shows us that you take this yellow times this yellow to get this. And that's the dot product of this and this, although we haven't talked about dot product in this in here yet. And then to get this one, you take the dot product of this and this to get that. And that's exactly what this is. This is a dot product. For example, it could be the dot product of this and this to get this. That is, if this is, see, if this is what? This is a 1 comma 2. So if this is 1 comma 2, then to get the result, you take this dot this. Okay, the next thing they talk about is matrix vector multiplication. Well, we already defined matrix, so if we want to multiply a matrix times a vector, we can think of that vector as a matrix, and then we can do this matrix multiplication. So in other words, we're thinking of the vector as a matrix. So they say we may consider a vector x in Rn as a matrix of size n by 1. So if this is n by 1, then A has to be something by n. So they say it's m by n. And then we can do this multiplication, and the result will be an m by 1 result, or in other words, it'll be a vector with the number of rows of that vector as m, where m comes from the size, the number of rows in A. Okay, now they remind us that in the last section, we saw that a linear map can be represented as a matrix, and vice versa. A matrix can be represented as a linear map. So what we're doing here again is doing a linear map on X. And we will see that when we construct neural networks, we take the weight matrix times a vector. So what does that tell us? That part of the process of the neural network is a linear map. Okay, next they just review the dot product. So we have two vectors, and we want to multiply them using this symbol, and we call that the dot product. And what it means is you take the first element of x times the first element of y plus the second element of x times the second element of y, and you keep doing that, and then you add all of those up. So that's what's happening here. First element of x times first element of y, because that's I equals 1. Then put in I equals 2, you get second element of x, second element of y. To keep doing those multiplications. And then this says after you've finished going through all of them, writing them all down, put plus signs in between there and add them all up. And that's called the dot product. And we can also write this, if we think of x as a matrix, then we could take its transpose, and we could write xt, x transpose y, or also y transpose x. Okay, now this is a little bit strange because they keep doing things backwards, because they mention the dot product. They don't define the dot product here. I say they define the dot product here, but they mention it earlier. Now same thing here. They use the transpose, but they define it afterwards, or they review the definition of it afterwards. But this is supposed to be a review, so I guess they assume that you've seen this before. So anyway, the transpose of the matrix A. So what does that mean? If A is an m by n, then it's like if you sort of flip the matrix, and you'll get, when you do that, an n by m matrix, and that's called the transpose. And what is this saying? this is saying, well, what are the elements of the transpose? Because here's the transpose, and what is this little ij doing there? That's saying, here we have the transpose, that's a matrix. And we're always allowed to put ij at the bottom to indicate the, in this notation here, this is this book's notation, you're always allowed to put ij against the matrix, against any matrix, to talk about the elements of the matrix, the specific elements of the matrix. Well, AT is a matrix, so you can put ij next to it. So when you do that, you're asking what is the ijth element of this matrix, and the answer is, given here, it's the jith element of the original A matrix. So let's look at that. Here's A, B, C, D, E, F. When you take the transpose, you get this, A, B, C, D, E, F. So this row becomes this column, and so on. So they're asking, like, what is the, what is this here? How do we get this value here? It's B, but I mean, how can we explain that? Or how can we show that in notation? So we're asking, if this is the transpose, we're asking what? For the 2, 1 element, right? This is in the second row and first column. So we're asking, for example, what's the 2, 1 element of the transpose? And the answer is, it's not the 2, 1 element of this, but the 1, 2 element of this. So the 2, 1 element of this is the 1, 2 element of this. What is the 1, 2 element? 1, 2, it's B. So that's right. So the 2, 1 element of this is the 1, 2 element of this. That's what they're saying here. The ijth element of this is the jith element of this. So that's giving us kind of a roadmap about how to get the elements of this. You take the, if you want to get the ijth of this, you get the jith of this. Okay, next they talk about what is meant by a symmetric matrix, and that's where AT equals A. Well, if AT equals A, then A must be square, right? If it's not square, then AT is never going to be equal to A, because it won't even have the same size. So at least the necessary condition is that it's of the same size, but that's not all we can say. That's not all that's meant by the fact that it's symmetric. So to be symmetric, a matrix has to be a square matrix, but then we can also say that its transpose is equal to A itself. So here is a symmetric matrix. What does it mean? It means that if you take the first row, then the transpose will have the same first row. So what does that mean? That means that when you put this down here, when you do this here, if you go down this way, you should have the same thing as when you go this way. And if you take this row, it should be the same as this. And when you have this, it should be the same as this. So basically, it's like you have a mirror image of what's happening up here over here. And they illustrate that here in Wikipedia like this. Like this element and this element are the same. 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 And so on. So again, this is the definition, but this is kind of the visual idea of it. Or you can also focus in on the individual elements. So we just said, for example, this element and this element are the same. So that means that if you take what is this element compared to this element? This would be Aij, for example. Then this would be Aji. So we can say that Aji is the same as Aij for every I and j. By the way, this Wikipedia uses a more standard notation for the individual elements. They don't use a capital A, Ji. They use a little a, Ji. So that's more standard than what we're looking at. That's more standard than using the capital A. to indicate the individual elements, but here he's using the capital A. Okay, so we have a square matrix, I'm sorry, a symmetric matrix, and next we have a square matrix, and that's just a matrix where the number of rows equals the number of columns. So it's a square matrix. And then we have something called a diagonal matrix. So here's an example of a diagonal matrix from Wikipedia. You can see that everything is zero except for along the diagonal. And then we have the identity matrix, which actually is a diagonal matrix. And it's the diagonal matrix with ones down the diagonal. All ones down the diagonal. And we know that when you take any matrix and you multiply it times the identity, you get the same original matrix back again. The identity matrix is the matrix which doesn't change the given matrix when you multiply the given matrix times the identity.